technology regarding the water shut off. And then we also very grateful to have Pak Dr. Firman Shah from Pertamina Drilling Services to talk more about the drilling operation. So we hope that we can inspire the young professional, the students, to explore the cutting edge technology, to connect them with the industry, with this enhance and create hands-on opportunity in the learning and innovation phases. Over the past year, our teams like Mbak Yunita and also Dandi, we work hand in hand to increase the awareness and about the sensor system, the programming, the robotic part, collaborative project that integrate the robotic application within the energy related application. So today's seminar will continue that journey, and then you will hear from our speaker today their activity, their research, the application about the technology itself. And then I'm very proud to share that Mbak Yunita and also Dandi is also excited, like all of us, to announce and then to share how we can take a lead this robotic and autonomous technology within our Asia Pacific. I hope that today's session will spark the curiosity. I hope that today's session will inspire a collaboration and motivate everyone among us to push the boundary what is always possible. Whether you are already as a passionate, robotic, or whether you are having some curiosity in this area, I encourage you to absorb the knowledge from our speaker today. And then once again, thank you for joining our event. And thank you to everyone who worked tirelessly and to make this seminar become reality. With that, let us begin with our program. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh.
Okay, I give to Mbak Yunita and also Dandi to lead our today event.
All right. Thank you so much, Dr. Ardian and Koda, for the talk today that welcoming the students, young professionals, and also the SPE board directors that are coming. Today we are having a very good seminar. Title is Advancing Technologies and Sustainability in Oil and Gas Operations. We will have Dr. Pirmansyah and Mr. Hedi Suherdiana as a speaker. So we're gonna have Dr. Ardian and Koda as well for the officially opening the webinars today. So let's start with this very quick reminder to everyone that using a virtual background that we have shared in SPE Asia Pacific's webinar once in WhatsApp group. So please use it and open your camera to have an excitement for today's agenda. And first of all, I would like to introduce Dr. Ardian Koda as a SPE director of the Robotic and Autonomous System. And I would like to him to officially open. If we have a cutting session, this is a cutting session. So Dr. Ardian Koda, one or two sentences to open this webinar, Doctor.
Yeah, thank you so much, Dandi. The key for us is to enjoy, right? To enjoy our event and then to take, learning as much as possible. And then we will follow up from our event today to create much more stronger community. Myself, Mbak Yunita, and also Dandi, we will create a follow-up event, hopefully early next year, to frame up and then nurture any, a face-to-face event where we can harvesting, let's say, a practicality of the application on the robotic and autonomous. So by this, let us start our webinar today, and then I wish all the best. Thank you so much.
Thank you so much, Dr. Ardian Koda, for the official opening of today's webinar, SPE Asia Pacific's Advancing Technologies and Sustainability in Oil and Gas Operations. We are having very great sessions today. With first speaker is Mr. Hedi Suherdiana, talking about water shut-off technology as a country lead manager, Saudi Arabia and Bahrain in flow control. First of all, I'd like to introduce myself.
Recording in progress.
My name is My name is Dandi Alfayed. I am currently a PhD scholar, PhD student in Kiev, UPM, Saudi Arabia. I've been author in several journals, SPE journals, international journals, and my expertise, my focus on PhD is that unconventional reservoir characterizations and advancing technology for the oil and gas operations. However, today's sessions is more about our speaker. One of the first speaker is that Mr. Hadi Suherdiana. About Mr. Hadi Suherdiana a little bit, he's a petroleum engineer with 18 years of experience in reservoir optimized completions and inflow control device. Currently, focus on getting the world energy needs with a less environmental impact by making better well hashtag with AICP technology. He's graduated from Institut Teknologi Bandung, ITB, in 2006 with a Bachelor of Science in Petroleum Engineering. As a professional highlight, he started his career with the Baker Oil Tools Indonesia in 2007 and then joined Chevron Indonesia Company in 2012 as a field engineer. And the same year, he moved to Saudi Arabia to rejoin Baker Hughes Completions. And right now, he joined Inflow Control ES, a Norwegian company focused on reservoir management technology, which he led and grow the business in Saudi Arabia and Bahrain to provide solutions for increasing water management problem and hashtag making better wells for Saudi Aramco, Babco, and Wapra joint. Above of that, he is a great author. He has published several SPE papers. One of the highlight is SPE 183383MS, which is included in September 2017 GPT, called Integrated of Bottom Cemented Inflow Control Device System Design Toward Well Delivery Optimization. So, without further ado, let's have a chit chat with Mr. Hadi. Hello, Mr. Hadi.
Halo, Assalamualaikum. How are you, Pak Dandi?
Waalaikumsalam warahmatullahi wabarakatuh. All good? How are you, Mr. Hadi?
Alhamdulillah, all good.
Alhamdulillah. All right, Mr. Hadi, without further ado, the screen is yours.
Thank you, Mas Dandi. Let me just share my screen. Can you see my screen?
Yes, we can see your screen.
Okay. Bismillahirrahmanirrahim. Rabbi shrah li sadri wa yassir li amri wa hlul 'uqdatam min lisani yafqahu qawli. Thank you everyone for your time. So today I'm going to talk about the autonomous water shut-off technology.
Sorry,
So
Hadi,
water
I think this is the wrong screen, yeah? Are you sharing? Sorry. Are you sharing the right screen or?
Yes, yes, yes.
Oh yeah. Yeah, thank you, Robbie, for I guess I shared the wrong screen. All right. Right. So water management is now a primary economic and environmental constraint in an oil production. So autonomous water shut-off technology has advances to the reservoir management by addressing produced water challenges proactively. This technology improves oil recovery efficiency while minimizing environmental impact through reduced water handling. So my presentation today will cover the technical backgrounds, also the field results of the autonomous water shut-off technology, and how the autonomous water shut-off technology enables sustainable and more environmentally friendly oil production.
Today, the oil industry produces 10 times more water than oil. Some wells are producing with water cut around 99%, meaning that for every barrels of oil, they're producing 100 barrels of water. This is crazy. Most wells will need an ESP pump to pump up the water. Maybe from 2,000 meters downhole, you use a lot of electricity, meaning a lot of CO2 emissions. Similar with the gas, it has to be flared. You have big systems for handling the water, handling the gas, separation, transport, all that kind of stuff. A lot of investment, a lot of operation costs, not required. It is possible to stop the water and the gas downhole. Today, we have the technology to do it. This is important, both for changing the oil industry to be more modern, but it will also be important for the world. We need energy, we need oil, and we need it in an environmentally friendly way.
Okay. So that was our CEO, Dr. Vidar Mathisen. So he was the founder and the inventor of the autonomous inflow control valve for AICV. So as he mentioned that 10 times more oil is produced when we are 10 times more water is produced when we try to produce 1 barrel of oil. This means we have opportunities that we can fix. The first one is to we can reduce the OPEX per barrel oil per day that is produced by us. So we know that water is heavier than oil, and lifting high volumes of water will consume significant energy, whether through electric submersible pumps or ESPs or gas lift systems. So this will increase the energy intensity per barrel of oil equivalent. And then the other opportunity is to minimize the capex for treatment facilities. So this meaning that the surface facilities must be sized to handle the total volume. So not just for the oil. So if we produce lots of water, we have to size the facility bigger to also handle the water. And also high water rates require larger separators, and then extensive filtration systems, and also chemical treatments to prevent corrosion and scaling. Plus, the disposal and reinjection of the water are often the most significant cost driver. For an example, the trucking of disposal for disposing the water to go to the saltwater disposal well can vary from $0.50 to over $2.5 per barrel. And then if we want to build a pipeline, it will cost more. And then the next one is we can extend uptime or the lifetime of the existing wells. So as for example, for new wells, like especially in carbonate wells, in carbonate formation, when we produce the well with an open hole completion, it will probably only last less than a year. With the autonomous water shut-off technology, we can prolong the plateau of the production. And plus, when we extend up the existing wells, we can reduce the walkover frequency, so we don't have to sidetrack more often. So before we go into the technical aspect of the water shut-off technology, we will discuss about the reservoir dynamics in horizontal well, because this is where the water shut-off technology will take place. So why are we drilling a horizontal oil well? So drilling a horizontal oil well will provide us with a larger and more efficient drainage compared to vertical wells. So we can access more of the reservoir and we can maximize the oil extraction. However, the horizontal well has several production challenges. The first one is the reservoir heterogeneity. In both sandstones and carbonate reservoirs, there are variations in permeability along the wellbore. In carbonate formation, the natural fractures further enhance the permeability differences. So these variations cause uneven fluid flow, which can lead to inefficient oil recovery and increased water production. I guess this is a familiar equation if you are a petroleum engineer. So this is the next challenge for horizontal well production, which is the Darcy equation that is governing the effect of the fluid when flowing through the reservoir. So the Darcy equation shows that the flow rate through a reservoir is influenced by several factors, including the differential pressure, the area, permeability, and viscosity, and the length of the flow. We will talk more about the permeability and viscosity in this case, because this is where the autonomous water shut-off technology will help. So reservoir heterogeneity causes imbalanced fluid along the horizontal wells, which leads to uneven production of oil, water, and gas. Why? Because oil normally has higher viscosity compared to gas and water, which makes it harder to flow comparing to water and gas. As a result, water and gas tend to flow easier through the high permeability zones, which oil flow is restricted. Plus, the horizontal well will experience a heel-to-toe effect. So what is the heel-to-toe effect? It's when the pressure drop at it's close. When the pressure drop is at the heel is higher comparing the pressure drop at the toe. So this imbalance is caused by the friction loss along the wellbore. So when the flow is coming from the toe to the heel, it will lose its pressure because of friction loss. And this will create more flow at the heel part of the well. So when you have more flow coming from the heel and less flow coming from the toe, water coning effect will be more likely to happen. Heterogeneity plus heel-to-toe effect equals non-uniform oil production. So in a horizontal well, from heel to toe, you will have non-uniform oil production, or the production will not be equal if you produce with open hole or standalone screen or whatever completion that is not using inflow control device. So how the autonomous inflow control valve will help in this case? AICVs, or the autonomous inflow control valve, will distribute the drawdown along the well. That means it will choke the place where it has a higher permeability, and it will give more way of flowing the oil at the lower permeability. However, when water or gas started to enter the compartment, when you have water and when you have water and gas started to enter, the AICV will create a choking effect and will create very high delta P, or higher pressure drop, and it will close the main valve. This also happened with gas. If gas is starting to enter, it will create a higher pressure drop in the compartment, which is eventually will choke the compartment. And all the drawdown that is given to this well will be distributed to the zones that is still dry or is still doesn't have water or gas. So we can produce more oil and we can increase the recovery factor of this well. So how does the AICV works? So as you can see here, we have the AICV cross section. The AICV has two main flow. Two flow paths. The first one is the main flow, which is producing 95 to 97% of the flow. And then the other one is the pilot flow, which is flowing about 3 to 5% of the flow. The fluid coming through the pilot flow is controlling the piston here, which is controlling the opening of the main flow. So for example, if oil goes into the pilot flow, it will create a pressure drop. So the pressure drop here is governed by this equation, which is mainly affected by the viscosity. So oil having high viscosity will create a high pressure drop in this laminar flow element, or LFP. And then when it's come out, and then when it's come out below the piston as a P2, so P2 will be lower than P1. The consequence of P2 lower than P1 the piston will be pushed down, and then the main flow will be open. So the AICV will be open for oil. And when water comes through the pilot flow, water having less viscosity will create less pressure drop or very small pressure drop inside the LFE. And when it come out from the LFE beneath the piston, it will be P2 that is similar to P1 because it doesn't lose significant pressure inside the LFE. However, because the force acting area beneath the piston is much larger comparing to the force acting area above the piston, and with this basic equation of the force equals the pressure times area, the force below the piston will be forcing the piston up, and it will close the main flow. So when water enters the AICV, it will close the piston, and then the piston will close, and then the piston will prevent the piston will close, and the water will be choked. The water will still come out from the pilot flow outlet here. So the AICV will close about 97% of the fluid flow, but still flowing around 3 to 5% of the flow. So the LFE here is acting just like a sensor. But remember, there is no electronics in this device. There is no control line to the surface. So this is purely fluid mechanics. And this AICV is reversible. When you start having oil again, it will start to open again the main flow, and then it will produce oil again. Okay, so we will see the video on the next slide. This is how the AICV is put in the pipe. See, when the oil is flowing, instead of flowing to the LFE, controlling piston. The main flow is providing choking effect like ICD. So if oil is coming, we provide the polarization effect like this. The AICV will open, oil is flowing. AICV will open for oil. There is another element here, different element. This will be useful if the oil and the water has a similar viscosity. When water started to flow, create a small pressure drop inside the LFP. So the P2 will be similar like P1, but because of the force acting area is larger, close the main. And it's reversible. When it comes back, it will open again. Same thing happens. Gas comes into the AICV. Gas which has a very low viscosity, with a very low pressure drop, it flows very well. And the AICV spoke gas production. Okay, so that was the theory. What about the real thing? Right. So what we have here is a simulation of water and oil flowing through AICV and ICD. So in the left side, we have the simulation device which we normally have in our exhibition. So we created the simulation by having a vacuum pump that is creating some kind of suction or drawdown effect that will draw down the water and the oil when it passes through AICV on the left side and also when it passes through an ICD device on the right side. So let's see what happens if we flow the water through the AICV. So we already turned on the vacuum pump. And as you can see here, the water is flowing very slowly through the AICV because it's being choked. The water is still flowing because it's still flowing through the LFP, like 3 to 5% of the flow. But when the oil starts to come inside the AICV, you will see the difference in the flow rate. So as you can see, the oil flow rate is much faster than when the water gets into the AICV. And then on the right side, we have the ICD. So ICD is a inflow control device, which is the traditional flow control device that has been used since the 1990s. So ICD cannot control water when it comes because it's just a nozzle. And you can see here, when we flow the water and oil, there is no difference of the flow rate. And this is how the AICV is placed on the joint. And there are several different sizes from 278 to 7-inch. We also have the super slim, which is the 238 size that can be retrofitted inside an existing ICD completion, 4.5 or 5.5. So if you have an existing ICD completion that already producing water, and you can expect there is still oil that is left behind, we can also put the AICV completion inside that ICD completion to produce the remaining oil that is left behind. And this one is the flow performance of the AICV in multi-phase of oil and water. So the AICV will start to choke the water at around 20% water cut. Gradually, the more water cut, more choking effect you will have. And on the right side, you can see that the ICD is not choking that much. Also for the gas, the AICV will choke gradually when the gas volume fraction or the GVF is increasing, while the ICD will produce more gas. So today we have various kinds of AICD or autonomous inflow control device that is market. And we have some studies to determine the performance by having this fluid performance ratio of or FPR. So what is FPR? So FPR is a calculation to compare downhole inflow flow performance percentage. So in short, if you want to compare between one technology and the other, you can use this kind of calculation. It's a simple calculation. You just need to know the flow performance chart of each technology that you have. Then you can compare. For example, this is a AICV flow performance chart where you have on the y-axis you have the differential pressure, on the x-axis you have the flow rate. So the AICV performance chart will have, all the inflow control performance chart will have the gas, water, and the oil flow chart. In this case, if we produce at 150 psi differential pressure, when you have 100% of gas, the AICV will flow around 22 barrel per day, reservoir barrel per day. And if it is producing water, it will produce around 30 reservoir barrel per day. If it's producing 100% oil, it will produce around 74 barrel per day. So what is the water reduction or the performance ratio of water in this case? Is the water flow rate divided by the oil flow rate, which is 30 divided by 74, equals about 0.4. So the water reduction is around 60%. Same to how to calculate the gas performance. The ACV can reduce up to, so for this one, it can reduce to 70% gas flow rate. For the ICD, when the ICD is producing water, it will produce around 68 barrel per day. And when it's producing oil, it will produce around 74 barrel per day. So the water reduction is only 9%. However, the gas production will be increased to 163% if it's producing gas. So you can use this method to calculate the performance of different autonomous inflow control technology. The AICV cannot work by itself. So the AICV has to work as a system. And part of the system is the annular isolation or packers. So this is the importance of annular isolation in AICV completions. Here you can see that the AICVs is run as a lower completions with several packers, and we create compartments. The more compartments we have, the more effective the completion. So as a comparison, if we have 1, 2, 3, 4, 5, 6, 7, 8 compartments here, comparing to 4 compartments here, what will happen if we start producing water? So in this case, the initial condition, everything is oil still. But if we start producing water, compartment in a completion where you have more compartments, the water will be isolated, and you will still be able to produce produce oil from the dry compartments. However, with the last compartment, even the area that is producing oil will start to choke because this annulus is not isolated and it's just acting like a highway. So water will enter also into this compartment, and the ACV will start to choke. So you will leave the oil producing from the half of the reservoir. Right. So what have we done in this in globally for the AICV? So we have several case studies that showing how AICV can help for us to make better wells.
What if water wasn't the oil industry's largest product? With AICV technology, 4 billion litres of water was saved from production in 2020. That's 4 billion litres of water not extracted from the earth. 4 billion litres not needing chemical treatment. Not transported and discharged back into the environment. These are the results that matter, not only for the oil and gas industry, but for the world.
Okay, the first case study is that we have deployed this technology in the Middle East, and then the reservoir is carbon formation with light oil 1.8 centipoise. So we initially this well was shut down because of a high water cut. So we retrofit the ASCV inside 8.5-inch open hole with 5.5-inch ASCV joints. And for the result, the water production reduced up to 66%. And then we have some savings from the operator, and we allow the prolonged oil production plateau for this well. So we increase the lifetime of this well. We reduce this much of water, and then reduce this much of CO2 per year, and this is similar effect to reducing about 40,000 cars per year from the road. The next case study is in 2023, also from the Middle East. Similar type of oil, but on this one, we increased. So this well was producing about 90% water cut, and then it was shut in, and then it was revived when we deployed the ASCV. So it was initially producing, but then the water cut came up very high. Then we retrofit ASCV to this well, and we reduce the water cut up to 50% water cut, and we triple the oil production. So this is the amount of water that is reduced per year, CO2, and also the cars that can be removed. Another one is the case in the Middle East for fractured carbon with 2.6 centipoise. So again, we have two wells here. These wells also were shut in. As you can see here, it was shut in because of very high water cut. The water cut was almost higher than 90% for both of for this well, and then about 60% of the for this well. On the first well, you can see that we revive the well after deploying the ASCV and suppress the water cut to around 30%. And for this one also, we revive the production and suppress the water cut production. In this one, it was a heavy oil application. So ASCV can work from ultralight oil to heavy oil application. So we can we have a high range of application. In this one, this one is side-by-side comparison between well completed with standalone screen and ASCV completion. So the blue ones are wells that are completed with standalone screens. You can see the water cut is mostly is more than 90%, and the green one are the ASCV completions. So the distance between these wells are only like 400 meter apart. So we managed to increase the oil production and reduce almost more than 80% of the water cut. So this client had a limited water handling capacity, so they cannot drill more wells. By having the ASCV completions, we managed to reduce the number of wells that they can handle, so the client can drill more wells. This one is an application in North America for water control as well. So we retrofit the ASCV inside an unconventional completion. So at first, before the ASCV completion, you can see here that the water cut is quite high, and then the production of oil is very low. And then after the ASCV is deployed, the oil production increase, so they can continue the life of the well. And oil production increase about 500%. So the AICV is not only helping us to reduce water production. We also can help operators to reduce the gas production, the unwanted gas production.
Why does the oil industry tolerate routine flaring if it can be avoided? Using AICV technology, 35 billion standard gas tanks have been passenger vehicles being taken off the road for 1 year. That's the same as 119 wind turbines running for a year. That's the same as 2,907 square kilometers of carbon sequestering forest, an area 27 times larger than the city of Paris. These are the results that matter, not only for the oil and gas industry, but for the world.
Okay, so now we are looking at the gas shut-off application. This is one of the cases in the Middle East where we managed to control the gas production, unwanted gas production, in one of the well in Middle East. So this one is the ultralight oil application. The viscosity is around 0.45 to 0.65. Initially, before we deployed the AICV completion, this is a PLT results showing that this well is producing a lot of gas, up to 10,000 scf GOR. So the gas is mainly produced from the middle part of the well, and it makes the remaining of the well is not producing anything. So they drill horizontal well about 3,000 feet, but they only can produce half of the section. And then it was shut in because the gas production was very high. After deploying the AICV, as you can see here, post-AICV PLT is showing that the gas production is being suppressed. So the GOR is being suppressed to the what you call it solution GOR, and it allows the operator to produce the remaining of the well. So now you can see that the remaining well is started to produce. So the initial production that was not coming out before the installation of the AICV, now the middle section until the toe is producing oil again. So this well was revived, and it maintained stable production for about 5 years, and yeah, so it also reduced the GOR production. Then we have another case in the Middle East where we have the pre-AICV installation, where you have a very high gas production here, and then very low oil production, and the oil then after the AICV, the oil now is increasing, and the gas production is suppressed. This is another case study in South America for sandstone formation for quite thick oil. So you can see here also the gas production is high, and then after the AICV installation, the oil production is getting back, and then the gas production is suppressed. Right. So this is my last two slides. We have some resources if you want to know more about ICDs, AICDs, and autonomous inflow control valve. We have a YouTube channel, and you can learn from these videos, which is started by our CEO and our CTO, Dr. Vidar Matisen and Dr. Isma. And thank you for listening, and I'm waiting for your question if you have any questions, and you can scan this barcode if you want to have the link for the videos. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you so much, Mr. Hedi Suherdiana, for the comprehensive presentations about the autonomous water shut-off technology from the from the reduced OPEX until the recent development of the technologies is more comprehensive than I thought, more than I expected. We have several questions. However, we're gonna have the funnels after the second speaker. So let me share my screen to introduce